Welcome everybody to this afternoon seminar. Today we are happy to welcome Professor Raphael Hirschi from Keele University. Professor Hirschi actually comes originally from Switzerland, so he did his master in physics at the Swiss Polytechnic in Lausanne. But then he moved to do a PhD at the Observatory of Geneva, where he obtained his PhD in 2004, and he specialized in computer models of massive stars. He continued to do a postdoc still in Switzerland and at the University of Basel, but then after a short while in 2007 he moved to Keele University, where he got, after 11 years, he got a professorship in 2018. So Raphael is the lead PI of the SHINE project, which is funded by the ERC starting grant that he obtained, and which studies stellar evolution using a combination of 3D hydrodynamics and 1D stellar evolution codes. And so I suspect that the title has something to do with that, because it's successes and challenges in simulating massive stars in 1 and 3 dimensions. So please, Raphael, you have the floor.
Okay, thank you very much. Unfortunately, the ERC grant is over. Life after ERC grant is not too bad, but yeah, I definitely miss it, and will apply for more. You should be able to see my screen right now, and hopefully now you can see my presentation. I can't see.
I see you, but not your screen.
Okay, I forgot to press share then. Okay. Some system. Okay, now you can see my screen.
We see the table of elements, and now we see your talk. Excellent.
Okay, perfect. Yes, the ERC finished in 2017. Time flies, always. Okay, so I'm going to talk, as was mentioned, about successes and challenges in modeling massive stars in 1 and 3 dimensions. I just want to highlight 3 of my PhD students. So Laura Scott is in this call, so if her camera is on, she can wave now. I'm going to present her work on entrainment in 1D models. Etienne Kaiser, I'm not sure if he's around, but he's done the work on uncertainties linked to convective boundary mixing, which you might have noticed. And Federico Rizzuti, who is on the call, so maybe he can wave now with his camera, is the new PhD student who's working on the neon shell simulations that I will hopefully present towards the end if I don't run out of time. Okay, so I think we're okay. All right, I usually start my talks, seminars with answering the question, Keele is not Keele in Germany, but where is it? Because not many people know where Keele is. So we have the map on the UK on the left, and then we zoom in on the West Midlands. On the right-hand side, you have Birmingham here. You can all see my mouse, hopefully. And then we have Manchester and Liverpool, so lots of nearby, a strong football team. I'm a football fan, so always happy to discuss football. And Keele is kind of in the middle of those 3 major cities, next to the city of Stoke-on-Trent. And the area is famous for potteries. It's actually called the potteries, and in particular, the blue pottery from Wedgwood. At Keele University, we have exciting renewable energy projects. So we have hydrogen in our gas pipeline, which sounds dangerous, but it's not. And we have also the smart energy network demonstrator, which monitors energy usage across the campus. So you should come and visit if you have not done so yet. Okay, moving to science, I will first review the importance of stars, massive stars in particular. And then I will talk about successes and limitations of 1D stellar modeling. I will then talk about what I think is the way forward, combining and contrasting 1D versus 3D models of stars. I will then present our results on the multi-D models of convection in carbon burning. And at the end, just give you a highlight of what's to come for neon burning. I will then spend quite a bit of time on entrainment and talking about convective boundaries generally throughout the talk. I will finish with some conclusions and outlook. So while people are settling in, let's review the importance of stars. So first of all, stars are important as objects in their own right. Massive stars occupy the top of the HRD. So we have Wolf-Rayet. Well, we start with OB stars on the main sequence, and if stars are massive enough, or after the main sequence, they become red supergiant, which are very large in radius and also very luminous. And if we are near the top of the initial mass function, we can have luminous blue variables, which have extreme mass loss, or Wolf-Rayet stars, which are very hot and have strong winds. And I know some of you work on this. I will unfortunately not be able or have the time to talk about mass loss in this talk. Massive stars and stars in general are also important as progenitors of supernova. So we have 87A in the top right. In some extreme case, when we have strong rotation and magnetic fields, we can have so-called GRBs. And what is left at the end is a white dwarf for low mass stars, or a neutron star, or black hole for massive stars. And we are always interested in finding out which stars produce neutron stars and black holes. And now for a few years, we even have gravitational wave detections. So we find out when two neutron stars or two black holes merge. And I think this is kind of a recent revolution in astronomy, to be able to detect mergers of black holes in particular. So this slide summarizes, it's not the most recent version, but we see we have quite a lot of knowledge about neutron stars because we can see them or observe pulsars. We also have quite a lot of information on black holes from X-ray binaries. What is I'm most interested in the LIGO results and Virgo results is information about the most massive black holes, or stellar black holes, that we can observe in the universe, because there were kind of no other way of finding out about those. In particular, I think there are two questions about the occurrence of mass gaps. And I think there's probably no mass gap here between neutron stars and black holes. It's just a question of sampling. I mentioned some of the papers discussing the non-occurrence of a mass gap here. I'm also very interested in the so-called Penn stability supernova mass gap between about 50 and 150 solar masses, but unfortunately, I won't talk about this today. I know that some of you work on exoplanets, so that's my only slide on exoplanets. And obviously, in exoplanet research, we are interested in variations in the light emitted from the parent star of the order of 1% or less. So if we're interested in such small variations, other interesting physics like pulsation and convection appear in the data. So, and I think more and more exoplanet researchers would agree that our understanding of stars is now limiting our study of exoplanets. Stars started having a role very early on in the universe. If we look at the evolution from the Big Bang, about 400 million after the Big Bang, we had the formation of the first stars, which took part in the reionization of the universe and ended the Dark Ages. And from that point up to now, stars contributed to the universe in many ways. We have obviously radiative feedback, but we also have kinetic feedback through stellar winds and supernova explosion, as well as chemical feedback. So the first massive stars cannot be observed because they have a lifetime of millions of years, so they're long dead. But we can observe the signatures of the first stars via low mass stars that have a long enough lifetime. And in some rare cases, we can even see an explosion from very early on in the evolution of the universe. So this GRB 090423 occurred at a redshift of 8.3. So this is about here in the evolution of the universe. Furthermore, stars are important for nucleosynthesis. All the chemical elements that we know were mostly formed in stars. And for this, I really like the chart of nuclei to discuss this, so neutron number versus proton number. And we know that nuclear fusion produces elements from helium up to iron group. And if we want to produce elements beyond iron, we have to use neutron captures, either via the rapid process that can take place in neutron star mergers or exotic supernova, or the slow neutron capture process, which follows the value of stability. This is usually thought to occur in AGB stars, so some of you are also studying AGB stars. I spent quite a lot of time studying the so-called weak S process, which takes place in massive stars. This generally produces elements between iron and the first peak, which is strontium. But in some cases, at low metallicity, if stars rotate fast enough, we can break away from the strontium peak, and we're still not sure whether we can reach barium or lead. And this depends on nuclear physics, and brings me to the Ketek cost action. So as we know in science, it's very important to collaborate internationally. And the goal of this cost action was to connect people working on nuclear physics theory and experiment to astrophysical modeling, and finally to GC modeling as well as astronomical observations. And the reason why I mentioned that is that cost action, I think, are a great type of funding, and some of you might be in the Gaia cost action, and they fund collaboration visits, so you can go and visit somebody and get paid for your trip. In particular, COST has started to do virtual missions, so you know that we can't travel much these days, but they've started doing virtual missions, so you can be paid for virtual visits. So the Ketek cost action involved 30 countries in Europe, and is finishing very soon, this autumn, unfortunately. However, international cooperation will continue with the IRENA, and this is a NSF, so a US network of networks, and this will help coordinate research in nuclear astrophysics for many years to come, so until 2024. Now, what I really want to mention in that type of project is the new project that started this month. It's called Ketek Infra, and this is kind of next level from a cost action. It provides funding for positions, time on telescopes and supercomputers. In particular, I received funding for a postdoc to help people doing stellar evolution modeling to be able to calculate the nucleosynthesis for their simulations. So I think there would be definitely good candidates in Leuven to benefit from this opportunity. So we have funding to help groups doing nucleosynthesis calculations. So for example, somebody does MESA calculations, you can save some output from MESA and then use the tools we will provide to calculate the complete nucleosynthesis. So I would be very happy if somebody is interested in doing that. So we can discuss this after the talk. Okay, so I think we can all agree that 1D television models have been very successful and will always be successful at predicting the evolution, fate, and impact of stars. They also provide a theoretical framework of interpretation for observations, and they also create a bridge between astronomical observations and nuclear physics. So they are really important. And my favorite diagram for stellar evolution is usually called a Kippenheim diagram, or the official name should be a structure evolution diagram. And I'm going to use those diagrams a lot, so I'm going to spend a bit of time describing this. So on the y-axis, we have the mass fraction, or the mass coordinates. So we have the center of the star at the bottom, the surface of the star at the top. And as we go to the right, we evolve in time from the zero-age main sequence up to the core collapse. This is for 15 solar mass star. So there's going to be an iron core collapse at the far right. Now the colored zones correspond to a convective region, and I will explain the color later on. But as you probably know, massive stars go through 6 burning stages: hydrogen, helium, carbon, neon, oxygen, and silicon. And nuclear burning usually starts in the core, in the convective core for most phases, and then move into shells. So for example, in the case of carbon burning, we have convective carbon burning in the core, and then into subsequent shells. Then we have neon burning core, oxygen burning core, and then we have tiny neon shells, oxygen shells here, and it gets quite complicated, which I will come back to later on. But another point to make at this stage is that we see from the colored areas that convection takes place during most burning stages in stars of all masses. Okay, so what do we need to model stars with the stellar evolution code? You will most probably be all familiar with the stellar structure equation, so I won't review them. But then we have a long, interesting list of physical ingredients, from nuclear reactions, mass loss, convection, rotation, magnetic fields, binary or multiple interactions. And then we have to add to that list equation of state, opacities, neutrino losses. and including the metallicity dependence of all these effects. So you have experts working on topics like mass loss and binary interaction, so I will not talk about that. Today, I will only have time to talk about convection. Okay, so as I said, if we start with 1D stellar models, I described the advantages, right? We can simulate the entire structure of the star for its entire lifetime. And we can not only do that for one star, but we can do it for a large grid of models with different masses and metallicities. I'm generally happy when I do tens or hundreds of models, but probably some of you are interested in doing thousands or even millions of models. So we definitely see that 1D models will stay. However, models have to use parameterized physics, and the main simplification is spherical symmetry. So stars are a bit like this inflated cow. They're mostly spherical, but we see examples, for example, the horns of the cow, that some aspects do not fit spherical symmetry. Okay, and what is missing is self-consistent treatment of things like convection, rotation, magnetic fields, even opacities and binarity, and the interplay. So in my dreams, I do 3D stellar modeling, and the main advantages is we can model explicitly fluid instabilities, Rayleigh-Taylor, Kelvin-Helmholtz, turbulence, and we can also have, if you have a 1D simulation, generally you kind of have matter flowing up and down in the same place. So either things have to go up or down, whereas in a multi-D simulation, you can have things going up and down at the same radius. The main disadvantage, however, of 3D simulations is the computational cost. I'm going to show one simulation. It would have taken 85 years on this laptop that I'm using now, and it still took months of computing time on supercomputers, and it cost the largest simulations cost 100,000 euros, dollars, pounds. So it's maybe not as expensive as a satellite, but these simulations are very expensive. And therefore, we are limited to dynamical timescales. So the time step in a 3D simulation is limited to the sound crossing time. And this is because most of these methods use a time explicit method. And therefore, we often struggle to get the resolution we want. And also, it's not clear if we can get away from the initial conditions we start with. Okay, so what's missing from 3D simulations is we will never be able to have the full star or full lifetime in our 3D simulations. Another limitation is we cannot simulate at the same time the large scale, so this is the scale of the star, and the tiny scale where some of the microphysics like viscosity happens. However, in the concept in the framework of implicit large AD simulations, which are simulating large scale, this is an example from Herwig and Woodward. The idea is we let the numerics do the viscosity, the job of viscosity. I won't go into detail, but somehow this is okay because the turbulence cascade is bringing kinetic energy from the largest scale down to the tiniest scale, and where you lose and how you lose the kinetic energy and transfer it into internal energy at small scale does not matter that much. Okay, but so 1D models are not perfect, 3D models are not perfect. Therefore, the way forward is to take uncertainties in 1D stellar models, like the horns of the cow, and then take targeted 3D hydro simulations that study what's happening to the cow horns in more detail. Then we need to interpret the 3D simulation results into either a theoretical framework or some numerical extraction of information, and then put it back into the 1D code, and then continue what I call the 3 to 1D loop, or it can be called also 1 to 3 to back to 1D. Okay, so in this talk, I'm going to apply this loop to convection. So first, let's see how convection is implemented in 1D code. So in most codes, convection is treated using the mixing length theory of Bohm-Witens, and there are some updates from Canuto and Mazzitelli and others. And I have a huge respect for Bohm-Witens and people doing similar theories, because this MLT theory works quite well concerning energy transport, predicting order of magnitude of the convective velocities. However, there is one major weakness of these theories, is they don't tell us where convection should stop in the star. So for that, to determine the boundary location, the stability analysis, Schwarzschild or Ledoux criteria are used. And then a weakness of these criteria is actually that these criteria tell us where the acceleration changes sign rather than where the velocity changes to zero. But even if we use this combination and compare models to observation, I will come back to that later on, we see that there is not enough mixing in the models compared to observations. So what I like to call convective boundary mixing, CBM for short in the rest of the talk, needs to be added on top of these either Schwarzschild or Ledoux criterion in order to reproduce observations. So let's review the dominant or the main convective boundary mixing implemented in stellar vision code. The two main ones are penetrative overshoot and what I call XD overshoot. So the penetrative overshoot is what usually people refer to as overshoot. It was developed by others, but in particular at SAN, where we basically extend the convective region. I don't know if you can see my hand, but hopefully some of you can see my hand. It will be more fun to describe it with my hand. So we have the initial convective region with the Schwarzschild criterion, and when we basically move that boundary by a distance dOV, which is related to the pressure scale height, and the free parameter is called alpha OV. So therefore, since we consider that extra zone as convective, there is the same degree of mixing and the same temperature gradient, which is roughly adiabatic. The other main prescription used for convective boundary mixing is the exponentially decaying diffusion coefficient. So that's why I call it XD for short. The formula is here. It's from simulation of Freitag et al. In '96. And in this case, this is partial mixing, which decreases exponentially as we move away from the boundary. And that zone is generally has a radiative temperature gradient, not an adiabatic one. And today I will introduce entrainment as an alternative to penetrative overshoot and XD mixing. But what I would like to point out first before I talk about entrainment is that both the penetrative and XD mixing prescriptions are inspired by multi-D hydro simulations. So they are kind of a very good first step to include CBM in codes. However, we need more simulations and better models for CBM. Okay, so now I'm gonna rest my voice for a minute or so. I have a question for you. I was gonna do a Zoom poll, but I was too late to set it up. So I have a question for you is, how uncertain do you think the initial mass to carbon-oxygen core mass relation is? Or more precisely, what is the uncertainty due to CBM uncertainties, so convective boundary mixing? So you could create models with different choices, for example, Ledoux or Schwarzschild, extra CBM, no CBM, in terms of the initial stellar mass, giving you the same CO core mass in solar mass units. So I'm looking for answers in solar mass units. If you look at models that have the same final CO core mass, by how much the initial mass of the models vary depending on the choices for convective boundary mixing. So I'm going to give you a few slides to think about it before I reveal the answer from our study, but feel free to type your estimate in the chat. So I'm looking at an initial mass range in solar mass units, so just a number. Okay. Okay, let's look at the uncertainties due to CBM. And the first one I want to talk about is the main sequence width. So this is work by Castro et al. In 2014. So you have and the spectroscopic HR diagram. I won't explain it. It's a slight variation from typical HR diagram, but for today we'll just, I think somebody's microphone is on. Is there a question? Maybe not. Okay, so Castro compared a grid of stellar models on the left from the Geneva group. This is from Ekström et al. On the right by the Brott et al. Group. And what you see is the evolutionary tracks with the time markers for a given time. And the observations, you have the ZAM's position and the TAM's position. And what you really see is neither of the stellar grids of models are able to reproduce the mass dependence of the main sequence width. So the Geneva models use a kind of a small amount, 0.1 for alpha, for overshooting. So they do okay, and they're actually calibrated for low mass stars. So they do okay for low mass stars, but they underpredict the width of the main sequence for high mass stars. Brott et al. Models have been calibrated around 15 solar masses. So they do better around 15 or 12 solar masses, but you can see they overpredict the width of the main sequence for low mass stars and underpredict it for massive stars. Higgins and Fink tried to introduce a new plane called a luminosity mass plane, where they are trying to break the degeneracy between different aspects or input physics leading to mixing. In particular, they are able to distinguish between the effects of rotation mixing plus convective mixing from the effects of mass loss. So that's an interesting new idea of how to distinguish between different physical effects and the impact on stellar evolution. And what they find is alpha values of up to 0.5 pressure scale height. Now, many experts in the audience on asteroseismology, so I don't have a slide on asteroseismology, but from my understanding of the general picture of asteroseismology, we have alpha parameters up to 0.5 pressure scale height, and the equivalent F parameter from the exponentially decaying diffusion free parameter of up to 0.5, but I'm free to be corrected by the audience anytime. Okay, and then this was just on the main sequence, right? Now, if we move post main sequence, the uncertainties accumulate. So this is work by Martins and Palacios looking at HRD evolutionary tracks from different codes. Now, you might think that the difference comes from the fact that these are used different codes, but actually most of these differences come from different choices made concerning convective boundary mixing. So for example, Schwarzschild versus Ledoux, or amount of convective boundary mixing. And actually in Jones et al. 2015, we compared different codes and showed that if you use similar choices for convective boundary mixing, you can get very similar evolutionary tracks. Okay, in the chat, I don't see any guesses for the uncertainties due to CBM. Okay, so Matthias has put now 4 solar masses. Actually, I found a way to see the chat. So I don't know if anyone else wants to guess. Okay, we have another Matthias, 10. Okay, this is Joris 1. Okay, this is your last chance before I reveal the answer. Okay, Karen 5, 2.5, okay. Okay, so there are different measures in terms of uncertainties and therefore different variations. But in Kaiser et al., we looked at various choices for convective boundary mixing. So for example, using Ledoux or Schwarzschild and different amounts of XD mixing. And it was a grid of 15, 20, and 25 solar masses. So for this mass range, if we skip to the answer to the question, on the far right, we have variations relative. So the delta Q is explained here. And you can see you can have up to 70% variations in the CO core mass for a given initial mass due to different choices in convective boundary mixing. So the answer 5 was closest to what I would say. So in the case of this grid of models, a 15 solar mass model may behave as a 20 solar mass models due to different CBM choices. Now, I only have one slide concerning the black hole mass gap, and this is just to highlight. So there are experts in mass loss. Mass loss is pretty critical to make predictions about the black hole mass gap and the metallicity dependence of mass loss. But there are also uncertainties due to convection. And in this particular case, at low metallicity, what happens, this is the helium burning core, and the helium burning core convection region can interact with the hydrogen burning shell here on top. And in that particular case, reduce the CO core mass, and therefore lead to different predictions for the boundaries of the Penn stability mass gap. Okay, I think for time I will skip this one, but just to highlight that there are even more uncertainties, and the uncertainties accumulate as we go forward in the evolution, and therefore we have a very large uncertainties by the time we reach core collapse. So I probably spent a bit too much time on the uncertainties, but hopefully now it is clear that we have important uncertainties concerning convective boundary mixing in 1D models. So let's go and do targeted 3D simulations to improve the situation. The first question is like, where should we start? We see we have convection everywhere during the evolution of stars. Now I can reveal that the color corresponds to the Mach number color map. Okay, so we see that for hydrogen and helium burning, we have a blue color, which means very low Mach number. And this is hardest to simulate with hydro simulations. So while observers might think, why don't you start with hydrogen burning? While the difficulty is the low Mach number. If we move towards the end of the evolution to oxygen and silicon burning, you see that the Mach number goes up to about 1%. And this is therefore more favorable. And also the tools for supernova simulations are more suited to simulate the late phases. So that's why most 3D hydro simulations started in the very, very late phases. You also see that the envelope has got high Mach numbers, but difficulty in the envelope is the length scale. So here you see the log of the radius, 10 to the 11, 10 to the 13. So the challenge for simulating the envelope is the range of length scale. So because other people had done the late phases, and the fact that you accumulate uncertainties as you go along, we thought, let's go for carbon burning. And you can see here, we're going to go for this second carbon shell. And one advantage of this carbon shell, it follows the core helium burning. So there is very little uncertainty about what happens before this shell takes place. Okay, so this is a zoom in. And I think that's just to highlight the difference in time scale between 1D stellar evolution and 3D simulations. The length of the 3D simulation is shorter than this, the width of this red line. And you see that I've changed from a time scale of log of years to now hours. But if I just go back, you see this is log of time left, so that's 10 million years. And carbon burning is something between 1,000 years and 10 years. We now move into a scale of tens of thousands of hours, and the 3D simulation is not even covering the width of this red marker. But this is the point where we start a 3D hydro simulation. So we have carbon burning here. The color lines correspond to nuclear energy generation. So the peak of the nuclear burning is at the bottom of the convective zone. We have a stable region here, radiative zone, convective region, and stable region above. And we're going to simulate this with a 3D cube, where the dark blue shows the convective region. Okay, so we do that with the Prompt code. You can ask me questions about the code at the end of the talk. And we do this in 3D. You can also ask me why don't we do it in 3D, even though 2D simulations are much cheaper. And we do a box in a star setup. And you can see the cube here represents our simulation domain, because this gives us maximum local resolution. So these are complementary with work, for example, of Woodward and Herwig, where they take a 4 pi. This would be called a star in a box, but ours are box in a star simulations. Okay, so this is the setup. We have the 1D input structure where we have convection between these two red lines and radiation outside. And these will be snapshots from a 1024 cube simulation. So this simulation shows us the speed or the magnitude of the gas velocity. So if you follow the flow, generally a flow doesn't change its velocity magnitude so far. So you can see how the material is heated up at the bottom of the burning front, rises up, and then instead of stopping and falling back down, what happens to this flow is that it is U-turn and has quite a high horizontal velocity as it reaches the top. So it does a U-turn instead of stopping and falling back. And you see lots of interesting things happening. So Kelvin-Helmholtz instability is here on the left. And you also see something that looks like clouds. So there are waves being generated in the stable region. Okay, so this summarizes the difference. In 1D, you have a straight line. In 3D, you have first a deformed, so undulated boundary, Kelvin-Helmholtz instability, and gravity waves. Okay, so these are very pretty movies, but these simulations are very expensive, so we need to make the most of that. For this purpose, we use what we call the Reynolds average IvS analysis framework. And this is complicated and puts a lot of people off. But if you just think of the most basic aspect of that Reynolds averaging or so-called decomposition method, is to translate to separate a quantity, in this case W, into an average quantity and a fluctuating component. So I think if you at least remember that this is the first step or the most basic aspect of this method, it is not so complicated and easy to digest. But in the long term, there's like endless possibilities. So one example is to take the turbulent kinetic energy equation, apply this mean field separation decomposition, and end up with a mean field equation. I won't discuss the detail, but there are two terms, WBP, which is linked to pressure dilatation, and WB for buoyancy. And these equations will help us determine what are the key processes at play in stellar interiors. And we can then apply this to our carbon shell simulations. So on the left, you see the radius. So this is the convective zone will be a bit around this region. The bottom stable region is below here, and the top stable region is here. And the plot is a bit small, but these analyses, first of all, tell us what is the role of numerical dissipation or numerical effect in our code. And as I explained, in the ILES framework, we let the numeric do the viscosity. But this method of analysis tells us what role does the numerics play. In particular, how well do we resolve boundaries. So here you see a small spike in the numerical noise. And as we increase resolution, we get a smaller spike. So it enables us to check whether our simulations are converged. And if we integrate those curves throughout the domain, we can see the dominant terms that play a role in driving flows. And in this particular case, for carbon burning, we have WB, which is this one, which dominates, and the other one is the numerical dissipation. And it tells us that in carbon burning conditions, buoyancy is driving convection, and then turbulence cascade goes down to small scales and dissipates that energy into internal energy. What is then useful, and I won't spend too much time, is we can then compare carbon shell simulations at the top to red giant simulation of Viale et al. 2013. If we jump straight to the right-hand side, you see that there's not only one blue term going up, which is the buoyancy work, but there's also the pressure dilatation that plays an important role. So it tells us which processes are important. One of the key results of 3D simulations is telling us what is the shape of boundaries. So many of the future plots that I will show will have a zoom on the bottom boundary, here at the bottom, a zoom on the top boundary, and the convective zone is squashed in the middle, and we don't see it. So you see the convective zone goes from this point to that point. And in blue here, we see the composition profile in the 3D simulation in solid line, and from the 1D input Geneva model in dashed. And then in green, you see the similar profiles for entropy. So we see two things here. We see that profiles in 3D simulation are much smoother than in the 1D input model, where we purposely didn't use any smoothing function at the edge of convective zone. And also we see that the convective regions are larger than in this input model where we had no convective boundary mixing. So these differences show us that we need improved CBM prescription. So in order to develop a new prescription, in particular for entrainment, we varied the parameters of our 3D simulations. We did a resolution study for this type of model which I described. So we go from 128 cube to 1024 cube. And you can see qualitative difference between a low resolution job and large resolution simulations where we see much more details. And this looks much more like turbulence than a low resolution run. We also artificially, so this is not what's happening in the star, but we boost the luminosity, the energy generation rate of carbon burning from a factor of 1, so that's no change, to a very large factor. Now these factors seem large, but our default multiplication factor will be a factor 1,000. And this is to help us both having less computational cost and also more computing for our budget. Okay, so from the other main results from these simulations is how does the boundary layer evolve over time, and especially the boundary location. And as you could see in the simulation, we have fast horizontal flows at the boundaries, and this entrain matter from the stable region, both above and below. And therefore, we can track the position in radius of the boundary. So in this case, the convective zone is in between the two panels. So this is the bottom boundary, top boundary. And you see that the convective region grows both from below and above. And the different colors corresponds to different resolution. So we see, generally speaking, that the resolution is not too much of a problem. And what you have to pay attention to is that the scale is very different for the top and bottom. So even though it looks like the bottom boundary moves more than the top one, actually the bottom boundary doesn't move much and moves much less than the top boundary. And this is one of the key results that we have, is that the bottom boundaries of shells are much stiffer than the top boundaries. It's also a good reason why we do convective shells instead of convective cores in our simulations. It's because we can study two boundaries for the price of one simulation. So by just fitting or determining the slope of those curves, we can determine what we call the entrainment rate or entrainment velocity of the boundaries. Okay. And then we can compare the results of our simulations to the so-called entrainment law from geophysics. And this entrainment law states that the entrainment velocity, this VE, normalized by the convective velocity VRMS, is related to the bulk Richardson number, so this RIB to a power minus n. So generally n is 1. So the entrainment rate is generally inversely proportional, as you can see from this curve, to the bulk Richardson number. So what is this bulk Richardson number? It's a measure of the penetrability of the boundary. So it is a ratio of stabilizing potential to turbulent kinetic energy. So if we look at different boundaries, so we have the top boundaries in discs, symbol, different colors, and the triangles are the bottom boundary. You see that in general, as I explained, the bottom boundary is stiffer, so it has a stronger stabilizing potential, so that means RIB is larger. And as a result of a stiffer boundary, you have smaller entrainment rate. So that's why the dependence is like this. And by using different boosting factor in our different simulations, we can then see if our simulations agree with this entrainment law, and they do quite well. And for that, we determine a parameter A, which is a constant of 5%. So these are the results from carbon simulation. And here we have the results from oxygen simulation. So we see that it's not all the simulations agree. We don't have a single parameter of A and N, but roughly speaking, we see that entrainment rate, so the growth rate of convective region, is inversely proportional to this bulk Richardson number. Now, an entrainment velocity is not so useful in the one distribution code, but we can easily convert this entrainment velocity into an entrainment rate, so mass entrainment rate. And you see the same A times RIB to the power minus n. We just have to multiply it by a few factors. And then in the 1D code, we're going to implement this by having the entrained mass, or by how much mass the convective zone has grown by entrainment, by simply integrating the entrainment rate over time from the start of that convective region. Okay, so I'm realizing I'm using quite a lot of time. Thanks for your patience. We've gone from 1D uncertainties to targeted 3D simulations. We've then used these 3D simulations to establish parameters of the entrainment law. So now the last step of this 3 to 1D loop is to put this back into a 1D code and see what happens. But before I do that, I would just like to just recap the theoretical picture we have of the convective boundary right now. So generally, you have a convective core or convective region or convective shell in yellow, and you have another region which is stable, where you could have internal gravity waves. Now, our idea of a boundary, it contains two layers. One that is entrained, or this corresponds also to penetrative overshoot. This is a region that is kind of also part of the convective region, so the temperature gradient is adiabatic. But because if we look at velocities, right, in the bulk of the convective region, we have strong radial flows. So this is radial flows. And as we approach to the boundary, the flow U-turns. And at this point, in this region, we have strong horizontal velocities rather than vertical velocities. And because the top region is stable with no velocity, we develop a shear layer. So this time this is also called Kelvin-Helmholtz instability. Okay, so for the 1D model that I'm going to talk about, we purposely only looked at entrainment and didn't consider the shear layer. This will be part of the next study. Okay, so now let's look at what's happening in the models when we consider entrainment. So here we go back to the spectroscopic HR diagram. We have the results of Castro, the results of Ekström, which are also shown with models in blue. So these are alpha over of 0.1. And we have the Brott et al. TAMS indication here. On top of that, we see models including entrainment with factors A, either 10 to the minus 4 or 2 times 10 to the minus 4. And if you focus on the purple line and the crosses here, which is kind of the very end of the main sequence, and you join the crosses, the purple crosses, you see that the models with entrainment do a better job at reproducing the terms from observational constraint. In particular, they do not have a well-defined end of the main sequence for stars above 25 solar masses. So we consider that entrainment does a better job at reproducing the mass dependence of the main sequence width than traditional overshooting with a fixed parameter. So why could this be the case? So we go back then to explain this to the Bulk-Richardson number. So remember that the entrainment rate is inversely proportional to the Bulk-Richardson number. And if we look at the Bulk-Richardson number of convective core boundaries as a function of initial mass, we see that the Bulk-Richardson number decreases significantly going from low mass stars to high mass stars. So lower Bulk-Richardson number means higher penetrability. So it's easier to plow into those boundaries. And the reason for that is actually the convective velocities that increase with initial mass. And you can see the dependence purely of the convective velocity dependence of initial mass with blue dots, whereas the Bulk-Richardson number are shown in red. You can almost entirely reproduce this mass dependence by considering the dependence of convective velocities on initial mass. Now let's go back to convective cores. So obviously these are main sequence models, so we can look at the helium core mass by the end of the main sequence for models with different initial masses. So we also have something that some of you would consider as low mass, others as massive stars, but we have low mass models all the way to 60 solar masses. The blue disks are standard Geneva models with 0.1 overshoot. And then you have different values of overshoot, 0.3, 0.5 with orange triangles and green square. And then we have our two sets of entrainment model, A equals 10 to the minus 4 and purple 2 times 10 to the minus 4. So our favorite model are the A equals 2 times 10 to the minus 4. And if you look, for example, at the 15 solar masses, you see that the helium core mass of a 15 solar mass model with entrainment is larger than the convective core mass with a default overshoot in the GenEC model. And this is represented here, where you see the relative increase compared to the Geneva models with entrainment. You see that the effect is largest for lower mass stars. There is a but here. The main issue we have to understand is that A values, right? Remember, this is 2 times 10 to the minus 4. If you noticed earlier, for carbon shell, we have a value of 5%. So there's a big difference between the values we have from 3D simulations compared to 1D models. Okay, we're almost at the end, but I thought I'll finish with some movies before I bring my conclusions. So the next step is we've done carbon burning, oxygen burning has been done before. So what we are working now on is neon burning, and in looking in more details at the interplay between nuclear reactions and turbulence. So in this movie, you see the neon 20 mass fraction, and the color scheme highlights 10% variations in the neon mass fraction as a function of time. So this is a very similar setup to the carbon shell, but in this case for neon burning shell. So neon burning takes place at the bottom. Below the burning shell, you had core burning, so you have no more neon. On top of the convective region, you have a stable region rich in neon. So you can see how we have interesting features that cannot be reproduced in 1D codes, where for a given height, we can have different composition or different mass fraction of neon in 3D simulations. So the next step is to, let me just show you, not just look at neon, but we're going to consider more and more isotopes. So in neon burning, you produce oxygen, which is top left panel. You also produce magnesium and silicon. So our idea or plan for the near future is to do 3D nucleosynthesis, where instead of just doing nucleosynthesis in 1D, is to do some snapshots of nucleosynthesis in 3D. So I think my time is up. Let me just conclude. So 1D models are powerful tools to study stars and the impact in the universe. But as I've hopefully convinced you, they have still major uncertainties. The way forward to overcome these uncertainties is the 3-to-1D loop. I've shown you how we've done this for using 3D carbon shell simulations in the context of convection, shown you how these simulations follow the entrainment law. I've also shown you, and this is important, that the lower boundary of a convective shell is stiffer than the upper boundary. So you shouldn't use the same mixing distance or F value for upper and lower boundaries of shell. It is interesting and promising that entrainment, the 1D models with the entrainment law better reproduce the main sequence width. And I think we have exciting times ahead with groups like in Leuven doing asteroseismology, other groups like us doing 3D hydrodynamic simulations. We can explore physics, complex physics in unprecedented details, and we have more and more powerful computers at hand. So with this, I close my talk, and thank you very much for your attention.
Thank you very much, Raphael. It was a very nice talk, very clear. If there are any questions, please mention this in the chat, and I will call out your name. As usual, I will give priority to the younger colleagues. Any questions or comments or remarks? Yes, please, Cole.
Hi, Raphael. Thank you. That was very interesting, and I've been following your work and the work of your group for quite a while, so this was a very fun presentation for me to watch. I have a comment that is going to morph into a question at the end. So I am of the opinion that given the degenerate implementation of all these CBM mechanisms in 1D evolution codes, that considering the constraining power from observations, the estimated values of FOV or alpha OV end up just being proxies for the total amount of mixing present at the boundary. And to that end, the large range of estimated values that we see kind of makes sense, so that we don't reproduce just one value, or we don't always recover one value for these mechanisms, but a spread. To that end, do you think it's sensical to consider only one global entrainment rate in the 1D models that you're considering, even though there's a lot more phenomenon happening? For example, stars with different rotation rates at different points in the main sequence evolution, so on and so forth.
Yeah, so I'm sharing our general picture of the convective boundary, and it's obviously a complex interplay, and we have what I would describe as a penetrative or untrained region. We have a shear layer, we have internal gravity waves in the stable region. Obviously, when you add rotations comes on top of that. But in the Scott et al. Paper, we purposely only included entrainment and wanted to fix the value of the free parameters to see what happened, right? Because if we were to say, well, I want to include everything, then we would not see how entrainment works on its own. And what is interesting is entrainment does not change the shape of the boundary. It only changes the size or the mass of, or it doesn't change much the shape of the boundary. I mean, for a receding core, it could change slightly the shape, but it mostly affects the size or the mass of the core's entrainment. And we think, for example, this can be constrained by the main sequence width. Now, we obviously hope that asteroseismology will help us constrain other aspects of the boundary, like the shape. And our next group of models will only include shear or a combination of shear, which can be similar to the XD. But I agree with you, there are more things, but we purposely try to include or study one by one so that we know what's happening with this one or the other.
Okay, yeah, no, thank you. I would be interested in seeing how you apply this to binaries as well, eclipsing binaries.
Mm-hmm. Yeah, I forgot to say it. I mean, for me, I expect the theory of convection not to change if we have, or not to change much depending on the mass of the star. So what changes when you change the mass of the star is, as I said, the convective velocities are different. But for example, the entrainment law, I would have hoped that we don't have to change the parameters. Now, it might not be the case, and we have to understand why. In terms of single stars versus binary stars, I would expect those prescriptions to be the same. Obviously, binary interactions change the overall evolution of the star, but if I take a star in a binary system or not, it would only have indirect effect, but not directly change the way convection works, and definitely not the way turbulence works. Because actually all our simulations reproduce turbulence properties or what we expect from turbulence.
Yeah, we have you can either take something like the sample from the Torres et al. 2010, the Claret and Torres series of paper, or the one that our group led by Andrew has published, looking at some of the core masses that we get from that. I'd be interested to see how well the entrainment laws reproduce those core masses as well.
Yeah, I mean, I'm still puzzled why, from observational constraints, we then infer different values of mixing parameters. I mean, so something I didn't have time to fit in 50 minutes. I can just show you. It's obviously we do it with entrainment, right? And I explained briefly how we implement entrainment in the models with having this entrainment rate and then integrating it over time. So this is the entrained mass, that region that grows with time. But what I would call a very temporary fix would be to have a mass-dependent overshooting parameter. And we purposely didn't want to have an equation in the abstract or any text, but we put a fit to the dependence of overshooting with respect to initial mass that we would expect if models depended or behave like untrained model, or reproduce, for example, the main sequence width dependence on initial mass. So maybe a first step would be to check what happens to the models if we take an overshooting distance, and if you prefer to use the F parameter. Generally, most people would take a F parameter roughly a factor 10 or 15 times smaller than the alpha. So you could try to use this formula as a first step.
Okay. Yes, thank you. I think I've taken up my fair share of time with questions.
Okay, thank you. Then we'll go to Dominic.
Hi, Raphael. Thanks for that. It was very interesting. I'm looking for some advice. So in our models, when we go past the main sequence and we have this hydrogen shell burning, we don't really know what to set what I'll call the undershooting value should be from this shell. So we have a choice of setting it as 0, but I agree that it seems to be a lot stiffer than the overshooting. So should that be 0, or should that be just a fraction of the overshooting in the case of a shell?
Yeah, so obviously this is not the same scale. So you're correctly pointing out that it's much smaller. From the carbon shell numbers or work, we see that the like F values or alpha values are generally a factor 3 to 5 smaller below compared to above. So that's generally what we do in our 1D models. If we say what would be my best choice for kind of extra CBM mixing below, because we don't want to call it undershooting. So CBM below is a factor 3 to 5. So for simplicity, I generally say a factor 5 smaller for what would be F under.
And should that stay constant, independent of the shell burning phase?
Yeah, so this we don't know better yet. So I would just take the F above extracted from, let's say, if I had to build a 1D model set of F parameters, let me just go back to. So I would set the F above according to this formula, which depends on the initial mass. And then F under a factor 5 smaller. And then try to keep that unless I have other hydro simulations to tell me otherwise.
No, I'm not aware of any. That's why my question, I think. But no, that's very interesting. Thanks.
I think the only special case is the convective envelope, right? And I think there are some simulations for the convective envelope. So I think Falk-Herwig uses generally a larger value for F for under the convective envelope. And actually, the hydrogen burning shell is an interesting one, because depending on whether you use Ledoux or Schwarzschild, is it opacity-driven convective shell, or is it a nuclear burning-driven shell? Most of the models I've done were with the Schwarzschild criterion, and they were nuclear-driven. But if you use Ledoux, they are often opacity-driven, so they're above the nuclear burning region. So it's still question mark. But unless we know better, I would just try to keep things as constant as possible and just use those settings.
Okay, that's great. Thank you very much.
Okay, thank you. Then we have the youngest is Jun.
So you mean I'm still younger than Connie, huh? Thanks, Raphael, for very nice overview. I actually had a question, a little bit in my own curiosity about your 3D dynamical models and the modeling technique. So, I mean, when we do the 3D models of massive star envelopes and atmospheres and the outer layer, so to say, you know, we also have the opacity peak. I think you referred to it like opacity-driven convection, right? But it behaves very differently, because essentially the role of radiation, because it's radiation pressure supported envelopes, right? Mm-hmm. So just out of curiosity, how is this in these very deep regions? Do you need to consider the radiation at all? And in that case, how do you do it? It's
yeah, so I didn't have time to mention that, so thanks for asking. So I fully agree with all your comments that radiation would be critical if you want to simulate the outer layers. I think we can use a simple diffusion method for hydrogen, helium, carbon burning is kind of in between. But for the very late stages, the energy transport is via neutrinos. So we actually include neutrino effects or neutrino production rate, and we can more or less safely ignore radiative effects from carbon or at least neon oxygen onwards.
Okay, that's interesting.
But we have a collaboration with Fritz Röpke and his student Leo Horst, and we'll soon have we're soon going to publish 3D simulations of the helium burning shell. And for the helium burning shell, they included the radiative diffusion, so radiation effects.
Okay, that will be very interesting. Thanks.
Okay, and then please, Tony.
Thanks, Raphael, for obviously very interesting talk. I have a practical question for you. What would be your favorite way that we improve our astroseismic modeling? And so, as you know, we are mainly still for the moment focusing on the main sequence because we have to start somewhere, and the seismic data is just much better there for the time being than anywhere else. But in this latest study that came out last week, which I discussed before with you of my Peterson's thesis, we try to see how the core mass changes as a function of which property of the star. And so for the time being, we see that it depends mostly on rotation, but not completely, because the correlation is not so strict as we would perhaps have anticipated. And so it doesn't seem to depend so much on the evolution time across the main sequence, right? So my question to you would be, have you looked at the time dependence? I know this is a very difficult question because the time scales for you are very, very different in terms of evolution versus your simulation time scales, but is there any prospect of assessing the time dependence of your model?
Short answer is yes. That we've done this actually with the 1D code. Okay, there are always some numerical glitches, but we think they're not critical to our models. But basically here, what you can see is evolution of the structure from 0 age main sequence to the end of the main sequence, so as a function of age. And I think that this is what you were asking about. And we see, for example, the time dependence of the stiffness of the boundary, and time evolution of convective velocities, and therefore by how we expect maybe how we expect the entrainment rate to vary. In terms of overall entrainment, there are two studies. Ours, where we assume that the entrained region grows with time and that never goes down, right? Which is one unique way, and maybe not the best way. Time will tell. I think the interesting signature we have is we have the largest cores, helium core masses predicted with cumulative entrainment, the way we do it in this paper. Starritsin has taken a different approach where it's kind of an instantaneous entrainment distance, so some kind of time varying overshoot. So you could consider maybe either or both methods. But what we really like to use is this Bulk-Richardson number, described in the paper how you calculate it, and you can see that it gets stiffer for the start of the main sequence, because as you evolve from no chemical gradients to some chemical gradient, then that has a strong stabilizing effect. After a while, the entrained region is in the region where you already anyway have a chemical gradient. So from that point onwards, it doesn't get any stiffer. So I think we can use 1D models and try to predict how stiff they are, for example, using the Bulk-Richardson number, and that could help us study the time evolution of the entrainment or overshoot or other processes. in terms of what could be done. So yeah, I mean, for me, I think the work you do is very interesting, trying to combine all these different physics input. For me, coming from theory, I would like to see, well, let's assume you just use entrainment.
Mm-hmm.
And then you maybe do a mass-dependent or overshoot or entrainment.
Mm-hmm.
And you see what is the signature of that.
Mm-hmm.
And for example, when I see all these different values for inferred overshooting, is there any clear dependence on mass? From what I have seen in the papers, there is no strong dependence on mass. But I'm just wondering, for example, if the time-dependent extra mixing works better than a fixed value of overshoot, for example.
Yeah, but I agree with you. To do one step at a time in adding in complexity. But for us, starting from a real star, we have the problem that we can't do that because we need to estimate the rotation of the star, whether we like it to be present or not. So we quickly end up in a high dimensional space. But if there are reasons that you give here to what you're telling me is, I think if I digest your answer well, is give us an estimate of the stiffness in some way, and then we have made progress somehow in the guidance of the simulations versus observations, right?
Yeah, I think measuring the stiffness of the boundaries, constraining it.
Yeah.
And I think for me, it makes sense that a stiffer boundary will have less entrainment or less mixing, right?
Yes.
And this is why having something like entrainment law or parameters like the bulk Richardson number, I find them so useful. Is because if you establish a result in one part or one convective boundary, then if you just have a number, you can't apply that number to any other part of stellar evolution, any other region, because the properties will be different. But if we have measures like the bulk Richardson number, then we can at least say we expect more or less mixing in that region or that part. And our simulations of comparing and that's why it was also so useful to do a shell rather than core simulation, is we could really see that the convective velocities are the same for a given convective zone, right? But we clearly see that the bottom boundary is stiffer and has much less entrainment than the top. So again, it goes back to we have a clear correlation or anti-correlation between the stiffness of a boundary and the mixing across it.
Okay, good. We'll try to look into that. Thanks.
Okay, thank you very much, Connie. Okay, I don't see any other questions, so let me thank Raphael again. Thank you very much. It was a very interesting talk. I just learned